Hi everyone, let's take tonight to review the concepts that we talked about in class on Monday. So we talked about the fact that there are variables that describe a gas, and there are three properties of the gas. So we introduced this idea of pressure, volume, and temperature, and the relationships that exist between the three of them in regard to gases. We introduced the idea of what is pressure, and that it's a force acting outward. It's a physical property. But there would be no pressure without collisions. So you really need those gas particles smashing into one another, because when they're smashing into one another, then they're smashing into other things, and you can measure the pressure that they're exerting. So the more collisions there are, the higher the pressure that the gas is able to exert. So just to reinforce, can there be pressure if there's no collisions? And the answer is no. And we even talked about a vacuum, and we spent some time talking about atmospheric pressure and the standards that, or the units that are used to measure atmospheric pressure. We talked about this idea that there's a barometer, and that the atmosphere pushes down and it raises the mercury within the barometer 760 millimeters, and as a result, we have, As a result, we have a tool to measure the pressure of the atmosphere. And you need to be familiar with 760 millimeters of mercury, 1 atmosphere, and 101 kilopascals, as well as the idea of 760 tool. So throughout the course of talking about the relationship between the variables, we came across this idea of Boyle's law. And we spoke about it in a very casual way. Some of the videos I showed you, some of the demonstrations, and some of the animations made reference to Boyle's law. So let's talk more about what that is. So specifically for Boyle's law, there's a guiding question to ask yourself: how are pressure and volume related? So way back when, in the 1600s, there was a scientist. His name was Robert Boyle. And he was able to indicate and figure out that this fixed N, meaning the amount of gas, and this term moles we're going to talk about later, but it's the number of molecules, okay? So if they had a set number of molecules and the temperature was fixed, then he saw a relationship between the volume and the pressure, and let's look at what that is. So here you can see that Boyle's law really tells you that volume varies inversely with pressure. And we have to talk about what inversely means, and also we'll look at some of the symbols to represent volume and some of the symbols to represent pressure, and we'll talk about how they're represented visually, because you'll come across these things. Okay, so the fancy mathematical stuff is we would write the simple volume, and we would say volume relates, that's what this symbol is letting us know, inversely with pressure. And that's, again, when the molecules or the moles are held constant and the temperature is held constant. So understand the number of moles relates to the mass. So the mass, the amount of the molecules of gas, and the mass of the gas stays constant, and the temperature stays constant. But then we said the volume varies inversely with the pressure. So this varies inversely means that one quantity increases, the other decreases. And I think if you spend the time looking at the demonstrations we spoke about on Monday, you'll remember that, oh yeah, I understand this. Remember, we did a lot of demonstrations in class using the vacuum chamber. We changed the pressure, we lowered the pressure last week when we were talking about vapor pressure, to show you that if we lower the pressure, that water is able to boil at a very low temperature, because the atmospheric pressure has been lowered, so less vapor pressure is required to make that water boil. And we also put marshmallows in our vacuum chamber, and we lowered the pressure around them, and the volume increased. We put a little shaving cream inside of our vacuum chamber, and the air particles that were trapped inside both the marshmallows and the shaving cream, once the pressure around them was decreased, they were able to increase, so the volume was able to increase. And I'm going to hit play, and this will be another example of when the pressure around this balloon is decreased, you'll see what happens to the balloon. Okay, the volume of the balloon is expanding. So now we see all the demonstrations we spoke about. When the pressure went down, the volume went up. The marshmallow, when the pressure went down, it got bigger. The volume went up. When the pressure went down the shaving cream, the volume of the shaving cream got bigger. That balloon, when we decreased the pressure, the volume went up. We're also going to be able to take Boyle's law and set it up this way, where the initial pressure and volume will equal the final pressure and volume. So soon we're going to use this equation to make predictions and figure things out, because we'll be given scenarios when we're given initial pressure and volume, and maybe we're given a new pressure and we have to figure out what the final volume will become. But those problems we'll do and look at another day. Today, right now, I want you thinking about the relationship between pressure and volume and how it exists in gases. You might not have known it on Monday, but another thing we discussed was Charles's law, which again deals with some of the variables that affect gases. And let's look at what Charles's law is and see exactly how we discuss them. So the guiding question you ask yourself in regard to Charles's law is how temperature and volume are related. So again, two of the variables that are thought about and discussed when you look at gases. So back in the 1700s, you had this scientist, Jacques Charles, and he was really interested in hot air ballooning, which apparently was popular back then. So let's look and see what he figured out. Okay, so for Charles's law, the fancy symbols that are involved is this time you have volume is directly related to temperature. Volume varies directly with temperature. And again, the mass, the number of particles, the moles, are held constant, and they're represented with the symbol M, and pressure is held constant. So let's continue to think about and talk about the things that we talked about in class. Okay, so our conversations in class included, balloons from when you were little children, and what you know about balloons, and if you are, so did you ever notice when you were little that when you were at the party, your balloon was full and brand new looking, and if it was the winter time and you went outside, well, all of a sudden your balloon got all deflated and didn't look so good, and you didn't think your balloon was going to make it till when you got home. But you took your balloon in the house anyway, and all of a sudden you went in your house and, the balloon came back to life. So that's an example of Charles's law. Let's also take a minute and look at this demonstration. So there's a balloon in here, and it's on a hot plate, and this is constant pressure right here because there is this beaker with the water in it is being used to provide the pressure, pushing down, and there's the balloon in the beaker. So you see it's about 70 degrees Celsius, and then we're going to take this beaker with the balloon and the pressure on it, and we're going to put it in an ice bath. Okay, so the balloon is shrinking. The beaker on top sinks. So here you see that because this balloon was put in a colder situation, that those molecules got closer together, so the temperature affected the volume inside this balloon, and you can see it because this beaker went down because the balloon got smaller. So you got to observe that direct relationship that as the temperature went down, the volume of the balloon also went down. So this time, we're going to look at the equation for Charles's law. So this time you have the volume over the temperature of the initial situation, and then you have the volume over the temperature of the final situation. So this would be the example of when the temperature was warm and the volume of the balloon was large, and then when the temperature went down, the volume of the balloon decreased. So let's allow this review and introduction to the actual equations that are involved in both Boyle's law and Charles's law be our ending point tonight. Please make sure you fill out the notes that are associated with tonight's lesson. Thanks.